Formulating the right response to a rapid rise in power demand over many years of accelerated economic development in the Islamic Republic of Pakistan has become a critical issue in both political and economic terms. Therefore, since its formation in 1958, the Pakistani Water Power Development Association, WAPDA, has been engaged in a number of large-scale hydropower plant construction projects. This latest project has been rolled out across a vast region stretching from the village of Ghazi downstream from Tarbela Dam and located approximately 90 kilometers northwest of the capital Islamabad to the village of Barotha, located in the Attock district around 50 kilometers downstream. The project has been dubbed the Ghazi Barotha Hydropower Project, taking its name from these two villages. The project is a mammoth construction effort comprising three elements: an intake barrage creating a huge reservoir with water from the Tarbela power station at Ghazi, a power channel extending 52 kilometers, and a power complex constructed at Barotha. This is a visual record of salient features of the fabrication and construction of the 1,450 megawatt power generation system. At present, Pakistan operates thermal, hydro, and nuclear power plants. The country's total current power output is about 17,350 megawatts, excluding that of Karachi Electric Supply Corporation, KESC, with an output of 2,055 megawatts. Each type of power generation, accounting for the percentage, is shown here. Hydropower generation, excluding that of KESC, accounts for 37.2% of total generated power. Total power output by hydropower is 6,493 megawatts, more than 22% of which would be generated at the Ghazi Barotha power plant. Of the vast Ghazi Barotha project, the power complex, equipped with generators, a central control room and switchgear, consists of two reservoirs, or head ponds, at the north and south ends, as well as power generating facilities. The two reservoirs ensure a stable supply of water from the Indus River, the level of which varies greatly between seasons. The amount of water depends largely upon meltwater in the catchment areas. In the powerhouse, 5 generators were installed. Each generator has a power generating capacity of 322 MVA and a water intake pipe, penstock, 10.6 meters in diameter, to ensure ample volume of water for the pressure head, which is connected to the spiral casing of the turbine. Construction of the power complex area commenced in 1995 with the building of an upstream dam, followed in 1997 by the power channel. Then, construction of the power complex and the installation of the generators. Toshiba's role in the Ghazi Barotha power plant construction project was to design, manufacture, deliver, erect and commission the generator and its associated equipment. To ensure smooth and efficient progress of the project, Toshiba formed a company jointly with Mitsui & Company Limited. This is the Toshiba Keihin Product Operations, the key Toshiba fabrication plant for the project. Since manufacturing Japan's first domestic water wheel generator in 1910, Toshiba has supplied almost half of the country's generator requirements and exported many hydropower generation components to a variety of sites worldwide, mainly in North America, Latin America, Asia, and Eastern Europe. Cumulative production as of 2000 came to 54,174 MVA. Toshiba's excellent technical capabilities concerning both pumped storage and variable speed power generation have consistently kept the company at the top of its field worldwide. At the Pakistan site, Toshiba cooperated with local companies such as EKL and European American companies such as ABB under the direction of WAPDA to carry out the many tasks involved with installation of the generators. The first step in the fabrication of a generator is the design. Toshiba Keihin Product Operations employed modern computer systems such as FEM for analysis and developed optimum designs for complex components using CAD technology. The resulting CAD data was employed as CAM data in NC machines for fabrication of the components. The generators used in this project are of the low-speed, high-capacity semi-umbrella type. Each generator has an output of 322.2 MVA with 60 poles, an output voltage of 18 kilovolts, and a rotation of 100 RPM. During operation, actual load on the thrust bearings may rise to as much as 1,700 tons. So the latest Toshiba technology was employed in design and manufacturing of the bearings. Each generator is composed of a stator, rotor, and shaft, with individual parts numbering in the hundreds of thousands. For the Ghazi Barotha project, 5 generators were designed, manufactured, delivered to the site, installed, tested, and commissioned over a period of 5 years. Here you can see the piece punching process. The latest state-of-the-art press can run the entire process automatically from material supply to product delivery. 1,000 pole piece-punched plates were required for each pole, or around 60,000 pieces per generator. Shown here is the process used to assemble the iron core of a rotor pole. The pole core is made from a steel plate with superlative magnetic properties and mechanical strength that is sandwiched between two end plates before being bolted together. The pole piece was embedded in a groove on the top of the iron core in order to provide stable operation and to control abnormal voltage and increase negative phase capacity in the event of trouble. A damper winding, which has been formed by silver brazing the upper and lower edges of a bar onto a brass plate, is assembled with a damper bar. This shows the manufacture of a field coil. The field coil is formed by winding a copper bar edgewise. First, material for the copper bar is fabricated in the specified shape. The field coil element is then annealed. Now the annealed rotor coil is press molded by putting a mold inside the coil to adjust its dimensions and shape as desired. Paper with excellent insulating properties is affixed at each turn of the field coil for layer insulation, before heating and compression. After molding, the coil is sprayed with varnish to further enhance insulation. Finally, all coils are electrically tested to ensure reliability. A stator coil is formed from multiple parallel lines of fine square copper wire insulated with a glass bar, then half overlapped with mica tape and filled with epoxy resin to prevent deterioration caused by internal corona. This shows the vacuum pressure process used in vacuum treatment. To prevent deterioration caused by surface corona, the outermost coil layer is protected using semiconductive paint and by corona protection treatment using tape. Finally, the product is checked using various tests. Here, the bearing metal is being welded. To control rotor vibration caused by eccentricity and unbalanced magnetic attraction of the rotor, a guide bearing with excellent metal adhesion strength is used to support an appropriate point of the main shaft. The guide bearing is made by TIG welding white metal on a steel base. This shows press punching of a rotor rim. The rotor rim comprises a magnetic flux circuit that supports the pole even under free rotation, while providing most of the flywheel effect required by the water wheel. As such, it must be extremely durable and accurate. In the case of the Ghazi Barotha project, sector rim type rotor rims punched out of steel plate were employed to form layers, taking into account the large diameter required and transport restrictions. At the factory, rims were manufactured individually by automated punching using a 1,000-ton press. A total of 6,600 rotor rims were used for each generator. This shows manufacturing of the stator frames delivered to the Ghazi Barotha power plant. The diameter of each stator frame is a massive 16 meters. The stator frame bears the weight of the iron core and coils as well as various stresses. The stator frame is a vital part of the generator, designed and manufactured to support all of these loads. The frame structure is divided into 6 sections, and after completion at the factory is finally reassembled on site. This shows fabrication of a rotor spoke 12 meters in diameter. Toshiba has a vertical boring machine that can hold rotor spokes with a maximum diameter of 16 meters, providing accurate machining under stable conditions. Here we see welding of the rotor shaft. The generator shaft is manufactured by welding together a flange 2.8 meters in diameter and a 5-meter long body, followed by machining, which results in the final product weighing about 40 tons. Given the thick plates used for the generator shaft, submerged arc welding was employed. This welding method applies electric current to the flux powder applied to the base metal surface to heat and melt both the base metal and the welding rod. After welding, the product is examined by non-destructive inspection and then machined to greater accuracy. Shown here is the rotor shaft being machined. For machining, Toshiba employed a lathe with a shaft length of 17.5 meters, the longest at Toshiba Keihin product operations. Toshiba Keihin Product Operations was accredited to ISO 9001 in 1994. All components are designed to satisfy ISO requirements and are managed under the strictest product quality management system. Now, let's have a look at examples of non-destructive inspection. Here, a lower bearing bracket weld zone is subjected to magnetic particle testing. The testing is designed to detect any defects on the surface as well as several millimeters below the surface of the sample. For welded structures, the optimum welding method is applied to ensure the weld's integrity. This shows ultrasonic testing of the lower bearing brackets. With this method, ultrasonic waves are applied to the sample. A partial reflection of ultrasonic waves occurs at internal defects, thus enabling the location, the size, and degree of any such defects to be detected non-destructively. This shows penetration testing of the lower bearing bracket. Penetration testing is effective for surface defects, in particular to detect open defects on the surface. This is magnetic particle testing on the upper shaft weld. This method detects defects on the surface or a few millimeters below the surface. It is designed to detect any defects on the surface as well as several millimeters below surface of the specimen. Products of particular importance were inspected carefully under the watchful eyes of special inspectors from a third party commissioned by WAPDA. Here, radiographic testing films are being checked. In this method, a thick specimen is irradiated to capture on film any defects and ensure integrity of the product. Completed generator parts were packed carefully for shipment. Shipments from Toshiba Keihin Product Operations started in October 2000. with hundreds of thousands of parts being shipped over the following 3 years. For the Ghazi Barotha plant project, a total of 500,000 parts of various sizes were shipped in 6 lots. Transport of very heavy items and precision machinery was provided by a Toshiba Group company, professionals in safe and secure transport. The 12,000-kilometer voyage from Japan to Pakistan takes 25 days. Materials and components delivered from Japan were unloaded at the port of Karachi and transported by road 1,900 kilometers to the power plant site. Speedways, a domestic company contracted by Toshiba, provided transportation within Pakistan for materials and components. A total of 500 vehicles were mobilized to carry a total of 7,000 tons of cargo without incident or accident. In August 2000, basic construction of the power complex building was finished, and assembly and installation of the generators commenced. Generators are usually installed in the following steps. Packers, the stator sole plate, and the lower bearing bracket are installed on foundations prepared by a civil works contractor. The main shaft of the generator is then installed, and the stator and rotors assembled at the erection bay on site are installed sequentially. Here, assembly of the stator is proceeding in the generator assembly area at the erection bay. The 6 parts are assembled sequentially.
आपकी डायरी कब आ रही है? पिछले साल हमने दी थी, डांस वाली ने दफ़ा नहीं दी। एक डायरी आप जैसी भी आए, हाँ जी, अगर नहीं भी आए तो आप कहें।
Shifting it slowly and steadily towards the additional piece. As you can see, stator frame is finally assembled. This is center post assembly.
By means of highly precise alignment work, a cylindrical frame with a diameter of 16 meters is completed.
This is the center post you can see in the middle with the temperature gauge. I'll show you the temperature. Core stacking is in progress.
After alignment, the stator core plates are layered in order along the internal diameter of the stator frame. Stator core plates are made from an insulated magnetic steel that exhibits excellent magnetic properties. Approximately 130,000 core plates were installed in layers for each generator unit, a lengthy process requiring great concentration, care, and patience.
making preparation for the core loop test. As you can see, we are preparing gum cable around the core of the stator.
After installing the stator iron core, an activity known as a loop test was carried out. During the loop test, the stator is wrapped completely in cables and electrically heated to check for abnormal phenomena such as local heat. Insulating varnish is sprayed onto the surface of the stator iron core after its integrity has been confirmed via the core loop test.
We tied the cable and give protection wood. You can see the gum cable, rather excitation cable. See, this is the excitation cable. Varnish is drying at the moment. I'll show you a close look. You can see the stator core stack.
Here you can see the assembly of a rotor in progress. The major processes consist of assembling the rotor spoke, incorporating the brake ring, layering the rotor rims, building in the reamer studs, and centering the rotation shaft. To assemble the rotor into a huge ring, each of the rotor rims is cleansed and then layered around the rotor spoke's periphery by means of pole-by-pole displacement. The layered rotor rims are then firmly bolted together by inserting reamer studs into holes in the rim plates.
remonstrate आ रहे हैं. Now inserting remonstrate into pole supports. Okay. Next.
Yeah, better car.
Very good.
Shown here is the rotor after the rotor rim has been assembled and its surface sprayed with varnish. 60 poles are assembled around the outside of the rotor rim. As important electrical components used for magnetizing the rotor, the poles are taken into position and assembled one at a time using a special lifting tool. The rotor rim has a dovetail groove into which a vertically hoisted pole is inserted with great care.
See the lifted pole cord. Slowly and gradually coming to its position. As you can see, it is coming slowly and gradually. Coming very slowly.
The water wheel is lowered into place and the main generator components such as the stator and rotor are installed. This shows installation of the main shaft. The shaft, weighing about 40 tons, is carefully lowered into place using a special jig. The main shaft is brought into the plant site lying on its side due to height limitations during transport. After its surface has been cleaned, main and sub cranes stand the shaft upright using special lifting tools.
This is the lifting device you can see. This is specially made for the lifting of shaft and rotor. This is basically called liner for sole plates. From this liner we can level the sole plate. Now it's going to put another one. Rakho. See?
Here, the generator foundation is being built by the civil works contractor. This will form the base of the stator and requires correct positioning and leveling.
This is one of the sole plates. This is the sole plate you can see.
After the foundation for each stator base and lower bearing has been adjusted to level, Stator bases and lower bearings are installed at 12 locations.